This is the end, beautiful friend. This is the end, my only friend. The end of our elaborate plans. The end of everything that stands. The end, no safety or surprise. The end, I'll never look into your eyes again. Can you picture what will be? So limitless and free, desperately in need of some stranger's hand in a desperate land. Lost in a romance, wilderness of pain, and all the children are insane. Our children are insane.
Morning, everyone.
Come on, baby. Come on, baby.
All right, how are we doing? Questions? Morning, everyone. Questions before we begin? Well, Maria is asking, because the book does it slightly differently, right? The way I introduced the ratio and root tests were for series of positive terms only. The book does it slightly differently. They first introduce series with both positive and negative terms. And then they take the absolute value when you're doing the ratio and root test. But of course, you understand what's really going on, right? If you take the absolute value when doing ratio and root test, you're really checking for absolute convergence. So we'll see that happening. I'll point it out today, but that's what's going on there. Today is our last class. So unless there are specific questions, let's go ahead and jump into what we were looking at last time. Today's song was The End by The Doors. I'll have the same office hours today and Thursday, absolutely. Maria would like to look at the series. Negative 1 to the end, sine pi over n. Let's do that. I thought it was fitting as well, right? I mean, I hesitated for a while. There were other songs, and then DMX passed away. Yeah. You can use the book definition with the absolute value, absolutely. That's fine. Let's consider this. Let's consider this and let us check for absolute convergence. Right, because it is a series with both positive and negative terms. So check for absolute convergence. By looking at just sine pi over n. And you understand that this term is positive, right? I mean, you have to be careful. Might not have been, But this term is, Sophia? I just assumed this was common knowledge. Sorry, didn't want to announce it that way. I mean, that's fine too, absolutely. As I was saying, that the textbook starts by testing the alternating series test, and if it's not applicable, they go to the divergence test. I mean, so how should you go? If you have an idea of whether so how should you go? I mean, look, it's not a bad way to go. John, you're certainly welcome to stay. Consider this. So, I mean, look, first of all, understand that for n large, well, in fact, for any n, right, bigger than or equal to 1, this is bigger than 0 and less than pi, less than or equal to pi. So sign is going to be positive. And that's very important, right? Because we're checking for absolute convergence. So we took absolute value of the whole thing, and the only thing that disappeared is this. You don't need absolute values for this because it's always positive. And now what? Well, we did an example very similar to that, right? What are we going to do? We're going to apply limit comparison with the series 1 over n. And what do you know about the series 1 over n? What do you know about the series 1 over n? You know that this is a divergent p-series where p is equal to 1, less than or equal to 1. Absolutely. So let's do a limit comparison. Going to do the limit of one of them over the other. And as n goes to infinity, this goes to 0. Sine of 0 is 0. So this has the form 0 over 0. Maybe we can switch to x so that, we can do L'Hopital's rule. So this still has the form 0 over 0. And if we apply L'Hopital's rule, what happens? Derivative of sine is cos. Derivative of the inside, chain rule, right? So minus pi over x squared. And derivative of the denominator, minus 1 over x squared. The minuses cancel. The x squares cancel. And as x goes to infinity, this goes to 0. Cosine of 0 is 1, so the whole thing is pi. So this limit is pi. And pi is between 0 and infinity. So both converge or both diverge. This one diverges. So this series diverges by limit comparison. So we don't have absolute convergence. Right? The series does not absolutely converge. It might still conditionally converge though. So absolute convergence is out. Let us now check for conditional convergence. Using the alternating series test. How did we choose 1 over n? Well, this goes back to calculus 1, where you knew that as theta goes to 0, limit of sine theta over theta is 1. So if the argument goes to 0 at the same rate as the denominator, the limit's going to be 1. And here, this goes to 0 essentially at the same rate as 1 over n. Right? I mean, you could have done a pi over n here, and this limit would have been 1. That's the idea. So that's why we knew to choose 1 over n. So if I ask a question like this on the final, you have to know that you have to check for both. I'm not going to specify, right? So from now on, you know that if it's a series with both positive and negative terms, two questions arise. Does it absolutely converge? And if not, does it conditionally converge? And you need to check for those without me having to specify. Let's check for absolute, for conditional convergence using the alternating series test. Here, the limit as n goes to infinity, as n goes to 0, as n goes to infinity rather, this goes to 0, sine of 0 is 0. So we're already halfway done. All we need to do now is check that the term decreases. Katie is asking an excellent question, and we'll do it right after. So there you have it. Now we have to show decreasing, and you know the easiest way to do that is to take the derivative. If the derivative of this function is negative, then that function is decreasing, which will imply that the an is decreasing as well. What's the derivative? Derivative of sine is cos times the derivative of the inside minus pi over x squared. We already did it here, right? And now for x large enough, and right, I mean, that's important because if x is 1, this is cosine of pi, which is negative. And if x is 1, this is also negative, so the whole thing is positive. And you don't have the result you want. But eventually, if x is bigger than 2, this is going to be a number between 0 and pi over 2. So that cosine is positive. And this term is negative, so the whole thing is negative. And there you go. The two conditions for the alternating series test have been met. So this conditional converges. Now we don't know what it converges to, and that's the beauty now. Now that you know that this conditionally converges, then you can start trying to figure out what it actually converges to. Maybe approximating it, or doing other techniques to try to figure out exactly what. May is asking how we can just ignore the -1 to the n in all of this. Well, you'll remember that the alternating series test is for series of exactly this form, right? And it tells us that if the limit of an is 0 and the an's are decreasing, then this series converges. And in these tests, in these conditions, there's no -1 to the n. There's no -1 there. Consider this. Katie was asking, what can we use to compare? Right? Because, I mean, first of all, you can do the limit comparison, the ratio test. Ratio test will give you the answer right away. Ratio test will tell you that this converges. But it's a nice exercise to try to use the comparison test. Selena is asking, do we have to specify this, that this series conditionally converges only for n equal to 2 or larger? Well, it doesn't, right? I mean, it conditionally converges even starting at 1, right? I mean, this is true for n larger than 2. So here you have established convergence maybe starting at 3. Right? You have established convergence starting at 3, but the first 2 terms are finite anyways. So if you add the term when n is 1 and the term when n is 2, these are finite numbers. So it's not going to make the series diverge. Right? Again, it's only the tail end of the series that's important. For simplicity here, let's treat this as 0.5 to the n. Now we want to establish a convergence using the comparison test. And it's a very nice exercise. First, here's my claim. For n large enough, n is less than or equal to 1.1 to the n. Let's prove it. And we'll prove it the usual way by taking a limit. As x goes to infinity, numerator goes to infinity, denominator goes to infinity. This is infinity over infinity. We're going to apply L'Hopital's rule. Derivative of the top is 1, derivative of the bottom, 1.1 to the x. ln 1.1. As x goes to infinity, this goes to infinity. 1 over infinity is 0. So for large values of x, x over 1.1 to the x is close to 0. So it's going to be less than 1. In other words, x is less than or equal to 1.1 to the x, or n is less than or equal to 1.1 to the n for large values of n. And there you have it. That does it. That does it. So n is less than 1.1 to the n. And if you multiply the whole thing by 0.5 to the n, you get n times 0.5 to the n is less than or equal to 0.55 to the n. Right? Because this times that is exactly that. And since is a convergent geometric series where 0.55 in absolute value is less than 1, then the other series converges by comparison. I mean, of course, I should mention that this is bigger than 0, but there it is. Convinced? Katie's asking, the 1.1 could be substituted with anything greater than 1 to prove this. Well, you don't want to go too far, right? You're right that it could be a lot of things, but it still should be less than 1, right? So you don't want to multiply by something too large. Make it less than 2, strictly less than 2, right? Because 2 times 1/2 is 1, and then you're in trouble. Exactly. How did I know? Sean is asking, how did I know to use 1.1? Again, as Katie has pointed out, anything less than any number so that the product is going to be less than 1 is the idea. So it doesn't have to be 1.1. 1.5 is fine. Anything that makes the product less than 1. Can we always use this when x is large enough claim? Absolutely, absolutely, right? Because again, to establish convergence of a series, it's just the tail end that matters. So the first finitely many terms don't matter. It's the infinity. It's the large enough, right? So the last infinite few, that's important. Now, I don't want you to use these claims on an exam without proving it, right? So if you want to use this, then you should prove it. Why did we choose 1.1? Because it works, right? 1.1 times 1/2 or times 0.5 gives you 0.55, a convergent geometric series. As Katie and others have pointed out, it doesn't have to be 1.1. Anything less than 2 is going to work. Any number bigger than 1 and less than 2 is going to work in this case. Is there a way to generalize this method, as in finding what to compare the series to? Yeah. Well, I mean, if you have NaN where A is strictly less than 1 in absolute value immediately, then yes, you could. Yes, you can. Yes, you can generalize. And I'll let you do that. So here's my question. What must you multiply A by to get to make this work? All right, let's move on. Let's move on by going back to what we were doing last time. Constance is suggesting to multiply by 2. Already multiplying by 2 would have been an issue here. Right, 2 to the n would have been an issue. We're in trouble. And if you just meant the number 2 without the exponent n, then 2 is not bigger than n. So that's not going to work. We are using Stewart's calculus. I think it's a well-written book. Has a nice mix of easy and hard exercises. Any new material today? We're going to see something amazing in about half an hour. And then something amazing. Well, I mean, I assume the odds are pretty good because a lot of people are using that book. All right, consider this. All right, so first of all, it's a series with both positive and negative terms. So let's start by checking for absolute convergence. By taking absolute value of the whole thing. This is always positive. So when you take absolute value, this disappears. And this is what we are looking at. And what are we going to do with this? We're going to do a limit comparison with the series. What series? Thank you, Jean-Chen. What series? Right, the numerator is root n. The denominator, for large values of n, this 3 is negligible. So the denominator behaves like an n. Numerator, root n. So we're going to do root n over n. The 2 is fine, but it doesn't really play a role, right? So you can include it or not. Root n over n, which is 1 over root n, which is a divergent p series, where p is equal to 1/2, less than or equal to 1. So, blah, blah, blah. We're doing limit comparison. So, limit of one divided by the other. And you know what's happening. You divide it by a fraction, we're going to multiply by the reciprocal. Factor out an n from the denominator, right? This has the form infinity over infinity. The n's cancel out as n goes to infinity, 3 over n goes to 0, leaving you with a limit of 1/2. 1/2 is bigger than 0, less than infinity. So both series converge or both series diverge. This one diverges, so that one diverges by limit comparison. So the series does not, this is a limit comparison, yes. So the series does not absolutely converge. There is still hope for conditional convergence though. And as n goes to infinity, so here we're checking for conditional convergence. Right, you have two things to check, namely the limit goes to 0. And you can cancel these. And as n goes to infinity, this goes to 0. So the stuff in the bracket goes to 2. This has the form 1 over infinity, which is 0. Excellent. Half done. Now we need to check that the terms are decreasing. right? We need to check that this is a decreasing function, and let's take the derivative. So differentiate using the quotient rule. V prime minus u v prime all over v squared. Simplify this. Put the numerator over common denominator. So 2x plus 3 minus 4x over 2 root x, 2x plus 3 squared. Is everybody with us here? And this is 3 minus 2x over that business. So you see, this part is positive, square root is positive, so the numerator will be negative if 3 minus 2x is negative, or if x is bigger than 3 over 2. The eventually here comes pretty quick. As long as x is bigger than 3 over 2, we're good to go. So there we have it, conditionally converges. What do we want to do? Well, what I'm suggesting here is that if x is bigger than 3 over 2, then this thing will be negative, right? So numerator is going to be negative, denominator is positive, so the whole fraction is negative. In other words, your function is decreasing. Is everybody with us? Questions? Now, what I want to bring your attention to is the fact that in 16, you actually have an alternating series that's kind of hidden. User is asking if it converges for all x bigger than 3 over 2. That's not really the point here. The point is that if x is large enough, in other words, bigger than 3 over 2, the derivative is negative, so your function is decreasing, and that's the second condition in the alternating series test. So it's the series that converges, and we have established convergence for n bigger than 3/2, but of course a finite few don't matter. And there it is. And as Haroon suggests here in this question, cosine n pi, right, what is that? If you're starting at, if we write them out, if you're starting at 0, cosine of 0 is 1, and cosine of pi is -1, and cosine of 2 pi is 1, and so on. This is really -1 to the n. Right, so that's why I'm suggesting, well, not only does it oscillate though, it's actually exactly -1 to the n. If it had been cosine of n, then we would have had to make use of that oscillation business. So in other words, this thing is really -1 to the n and over 2 to the n. So as, I forget who now, was suggesting that in the book they do the ratio test with absolute values, whereas I introduced the ratio test just for series of positive terms. Both methods are acceptable, so let's do it using the book's idea. And let's apply the ratio test. Where they do the ratio, the absolute value of the ratio. And of course, since you're taking the absolute value, these things don't matter because it's just absolute value of -1. I want to say that it's -1 to the n, right? When n is 0, this is cosine of 0, which is 1. When n is 1, this is cosine of pi, which is -1, and so on. And it follows the same pattern as -1 to the n. It really wouldn't make much of a difference, but I believe this is correct. Right, so the book will just take the absolute value of the ratio, and that is equivalent to checking for absolute convergence. Is that clear, everyone? Is everybody with us? So let's flip that. This is 2 to the n times n plus 1 over n times 2 to the n plus 1. And this and that cancels. And we're left with 1/2 limit of n plus 1 over n. You can break that up into two things. And this is 1 plus 1 over n. And as n goes to infinity, this goes to 0. So we get a limit. How can we prove that cosine of n pi is -1 to the end on the exam. You should write down the first few terms, and that will be convincing enough. And sorry, I hadn't seen Selena's question, but Michael has answered that, so thank you. Sine of n pi is always 0. Very nice. So here, the limit is less than 1, so the series absolutely converges. And you know that absolute convergence is the strongest form of convergence. So we're done. There is, John, there is. I want to say it's one of the first in the series. Yeah. Oh, you mean, sorry, you mean with the ratio test? Yeah, it's called a ratio and root tests. All right, questions here? How are we doing? Here's a nice question. Show this series converges. How many terms must we add so that the approximation is to within 0.1235 of what the series converges to. All right. So show that this series converges. In fact, we can easily show, yeah, I mean the whole thing over n, right, though, Arun? There's an n in the denominator. What do we want to do? First, consider as Arun suggests, you may want to rewrite it this way. 1 over n of 3 to the n. It's fine. And we can check for absolute convergence using, so if we check for absolute convergence, you know the way I want to do it. Forget the -1 business, or you can do this. Both are fine. Are we really going to calculate that in the exams? Yeah, you should expect a question like this on the final. So we're gonna do this, and we're gonna apply the ratio test. Apply the ratio test, so we're looking at 1 over n plus 1, 3 to the n plus 1, over 1 over n, 3 to the n. So this is n, 3 to the n, over n plus 1, 3 to the n plus 1, and 3 to the n cancel out. And this is 1/3 n over n plus 1. Factor out an n from the denominator. The n's cancel. As n goes to infinity, this goes to 0. And we're left with 1/3. Let's finish this question, Tom, and then I'll answer your question. 1/3. What about 1/3? 1/3 is less than 1. So converges. The series converges absolutely. Well, somebody want to answer Tom's question? It does not converge. Arun is correct. It does not converge. And Michael has said why. It diverges by the divergence test. The limit is not 0, and we're done. The series itself does not converge. That's it. Well, let's finish that, and then I'll show you the issue. Right. So what have we done? We have established convergence, in fact, absolute convergence of this. But now we want to approximate. And we saw in, I don't want to call it the proof of the alternating series test, but one of the things that came out of the alternating series test is that if you have a series which satisfies the hypotheses of the alternating series test, then you can approximate and the error is less than the next term in line. So now we would like to make sure that this satisfies the hypotheses of the alternating series test. Yeah, we're not finished with this question. It's not. We're not finished. So I'm suggesting that we want to use the idea we saw in the alternating series test. So we need to make sure that this series satisfies the hypotheses of the alternating series test. Well, this is easily seen to be 0, right? Because this goes to infinity, that goes to infinity. 1 over infinity is 0. And if you consider 1 over x3 to the x, or x3 to the x to the negative 1, the derivative is negative 1, x3 to the x to the negative 2, times the derivative of the inside, which is a product, so product rule applies. 3 to the x ln 3 plus 3 to the x. Everything is positive here, except for the negative 1 outside. So it's easy to see that the derivative is negative. So the function is decreasing. And so the hypotheses of the alternating series test are met. So by this idea, we saw that what the series converges to, namely this, well, let's rewrite it. What the series converges to minus an approximation that you're going to do by adding the first n terms. This, in absolute value, is less than or equal to the next term in line. 1 over n plus 1, 3 to the n plus 1. Zoe is asking a good question. Why do we have to do the alternating series test as well as the absolute convergence test here, right? You know that the series absolutely converges. So of course it's going to converge itself. The alternating series test didn't need to be done. We already knew that it converged. But that's not what we're checking. We're checking that the hypotheses of the alternating series test are met so that we can safely say that the error is less than the next term in line. This is only true for alternating series. Right, so this is only true if the hypotheses of the alternating series test are met. And there is no negative 1 to the n here. So there it is. So now, if we can make this less than 0.0005, then we're good to go. And you know that this is a decreasing sequence. So as soon as it's true for one n, it's true for the rest. So we want the smallest value of n for which this is true. 10, 100, 1,000, 10,000. This is 5 over 10,000 or 1 over 2,000. So as soon as this is less than 1 over 2,000, you're good to go. And you can try n equals 3. So you have 1 over 4 times 3 to the 4. 3 squared is 9, that's 81. That's 1 over 4 times 81. 32, 4. That's not good. But if n is 4, you have 1 over 5 times 3 to the 5. That's 81 times 15. That's still not good. But n equals 5 is going to do it. You get 1 over 6 times 3 to the 6. That's 1 over 81 times 9 times 6 is 54. And this is about 1 over 4,000, which is less than 1 over 2,000. Right? You don't even need a calculator. You see that n equals 5 is the first value. So the sum from 1 to 5 of this approximates the series to within 0.0005. And what is that? Well, I mean, when n is 1, this is minus 1 over 3. When n is 2, this is 1 over 2 times 3 squared, minus 1 over 3 times 3 cubed, plus 1 over 4 times 3 to the 4, minus 1 over 5 times 3 to the 5. So if you add these 5 fractions, Juan, rather, there is no difference, right? Series are series. It's just that, first of all, not everybody has seen series in all their glory in Cal 2. So we redo them in Cal 3. And you know, I mean, we're stopping a bit short here. We're running out of time. And I mean, that's typical of Calculus 2. We never have time to do all of series. So it's good to do them again. But now with online courses, I think people are going to anyways, so let's not worry about Cal 2. Right? So, you know, I mean, if you add these 5 terms using a calculator, using Wolfram Alpha, whatever you want to do, you're going to get a value. And that value approximates this series to within 0.0005. Well, I mean, we're supposed to cover series again in 222. As you know, I'm teaching in the summer. So everything we've done will be assumed knowledge, and we'll pick it up where we left off. And move into Taylor series and so on. Exactly that. Questions? Well, I mean, this is our last class, right, Matthew? So, I mean, we have 20 minutes left, not even. Questions? How are we doing here? Anybody? I am, yes. 222. Questions? Let me ask you this. Oh, wait, before we do that, let's talk about, was it Taha that had this question? I forget now. Right, a lot of people have said that this is not a convergent series because of the divergence test, and you're absolutely right. This does not converge, right? 1 minus 1 plus 1 minus 1 plus 1 minus 1 and so on. This does not converge, right? I mean, you're thinking to yourself, well, if I group these two, these are going to cancel, and you get 0 plus 0 plus 0. So should it converge to 0? Obviously. But if you group them this way, then you get minus 1 plus 1, which is 0. And this is 0. And this is 0. So shouldn't it converge to 1? And you know, I mean, back in the day, they thought that this, right? I mean, if you start with 0, which is 1 minus 1 plus 1 minus 1 and so on, and then you group it the other way, you get something out of nothing. And, you know, I mean, some people liked to think that this was a proof of the existence of God, that you got something out of nothing. But, of course, you understand that this is nonsense. The series does not converge, so there's nothing you can really do about that. But let me ask you, what is 1 plus 2 plus 3? Well, you know what this is. And this is the same as 3 plus 1 plus 2, which is the same as 2 plus 3 plus 1. Right? Because you know addition to be commutative. It doesn't matter how you add the terms, because addition is commutative in the real numbers. Is that true, though? Is that really true? Does it matter, or doesn't it matter, how you add them? Right, and well, I mean, you have this flavor here where it might actually matter, but this didn't converge anyways, so there's no point in discussing this example. But let me bring you to the beautiful observation of Riemann. Consider, let AN be a conditionally convergent series, right? So it just conditionally converges. It does not absolutely converge. Observe that the positive terms can be represented this way. Right, let's make sense of that. Let's make sense of that. Right, you know that the absolute value of a number is either that number, if that number is positive, otherwise it's negative of that number. Right? So if you add an to this, well, it's either going to be 2an if an is bigger than 0, or it's an minus an. So it's 0 if you get the negative. In other words, this is either an if an is positive, or 0 if an is negative. So it just picks out the positive stuff, right? If it's positive, you get that value. If it's negative, you get 0. So if this is conditionally convergent, the sum is the sum of the positive terms. In the original series. Right? This is either 0 if the term is negative, or it's an if the term is positive. So this is the sum of the positive terms in the original series. And what is this? This is the sum of a convergent series and a divergent one. And we saw a while back that if you have a convergent series and a divergent one, their sum is divergent. So this diverges. But this term is always bigger than or equal to 0. So what does it diverge to? It has to diverge to infinity. This has to be infinite. If you repeat the argument similarly, the sum an minus the absolute value of an over 2 is the sum of the negative numbers. This is the sum of the negative terms in the original series. Right? You can do the same argument. Negative here, this is negative and positive. And when you add an, you either get 0 or 2an. And when you divide by 2, you still get 0 or an. So it's the sum of the negative ones. And again, this part converges, but that part diverges. So it's the sum of a convergent and divergent series. So that has to diverge as well. And what does it diverge to? It has to diverge to negative infinity because you're just adding negative terms. All right. So what? Right? If you have a conditionally convergent series, if you add the positive terms go to infinity. If you add the negative terms go to negative infinity. And here's the beautiful observation that Riemann made. Let an be conditionally convergent. Right, so this series converges to some value, whatever it might be. Right, so this converges to something. Let this be conditionally convergent and fix a real number b. Take any real number that you want. Then there exists a rearrangement of the terms in the series. That converges to be. And why is that? Well, you fixed the b. You fixed the b, and you know that the series of positive terms goes to infinity. So start adding the positive terms until you get to something bigger than b. And then start adding some of the negative terms until you get to something less than b. And then start adding more of the positive terms until you get to something bigger, and negative until you get to something less, and so on and so on. You see that you get a rearrangement converging to b. Example. The series -1 to the n plus 1 over n. We ran out of time, but you'll see in Cal 3 that not only does this, well, so first of all, this conditionally converges, right? Because when you take absolute value, you get the harmonic series 1 over n, which is a divergent p series. So this conditionally converges. I mean, I'll let you prove that. What does it converge to? We don't know. Not in this class. in Cal 3, you'll see that this actually converges to ln 2. This converges to ln 2. I mean, what is that? This is 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6, and so on and so on. So this converges to ln 2. Riemann's observation was that if you take any other number, any number that you want, let's say 17, we can switch, we can rearrange the terms here to have a series which converges to 17. And how do we do that? Well, you add enough of the positive terms until you get to something bigger than 17. Well, I mean, Ashlyn, let me illustrate with this idea, right? I mean, I'm suggesting that this series converges to ln 2. Ln 2, which is less than 1, right? So it's a small number. What I claim we can do is we can take all of these numbers in this series and rearrange them to have the sum now converge to 17. Right? You're going to take enough of the positive numbers until you get to something bigger than 17. And you know that's possible because the sum of the positive numbers, as we have shown earlier, diverges. So you can get to as large a number as you want. Once you've gone to something bigger than 17, start subtracting. Start throwing in the negative numbers until you get to something less than 17. And once you've gotten to something less than 17, then start adding the positive numbers where you left off until you get to something bigger than 17, and so on and so on, to get a series which converges to 17. It's the series with the same numbers, right? It's the same numbers. It's just a rearrangement of those numbers. Right? So when you're adding 1 plus 2 plus 3, you're thinking to yourself, it doesn't matter how I add them. You still get the same sum, but it's not true if you're adding infinitely many numbers. The order in which you add them makes all the difference. Isn't that amazing? How are we doing? Seems like a good place to end, doesn't it? Thank you all for coming, folks. Good luck on the final exam. I'll be available today and Thursday. Ashlyn, you start, so you add positive terms until you get to something bigger than 17, then start adding negative terms until you get to something less than 17, then continue adding positive terms until you get to something bigger than 17, and then more negative terms until you get to something less, and so on. So you see that you're getting ever closer to 17. The series converges to 17. The office hours are on Zoom. All right, folks. You guys have a good one. And I will see you in 222 in the summer. It only matters the order if the negative numbers are involved. Indeed, you need conditional convergence is crucial here, because if the series absolutely converges, then any rearrangement actually converges to the same value. Indeed. While this Riemann observation is not going to be on the final, but it's a beautiful piece of, beautiful observation. All right. You guys have a good one. And like I said, I've got office hours if you need to see me. Otherwise, good luck on the exam. We'll prove this again in 222, absolutely. And we'll pick it up from there. All right. You guys take care. Exactly that, Veer, right? Rearranging the numbers in a conditionally convergent series can change the sum. Absolutely. Absolutely that.